Uh, ma'am, unmute, ma'am.
Okay, okay. So now we can start. I think slowly the others will join. So good afternoon to you all. And then I welcome for the afternoon session of second day, the webinar on waste to energy. Now I welcome Dr. G.N. Nikhil, Department of Biotechnology, NIT Jalandhar. So Dr. Nikhil, so I screen share is fine. So Dr. Sushma, so can you introduce? Hello?
Yes,
Yeah.
ma'am.
Yeah.
Good afternoon, sir. Good afternoon, everyone. Dr. Nikhil is the Assistant Professor of Department of Biotechnology at the Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. His expertise is in bioprocess engineering with specialization in bioenergy and biofuels. Recently, he also received Bharat Ratna Kamraj Memorial Young Scientist Award in 2019. He has also published more than 30 research papers in reputed journals. Sir, I welcome you. On behalf of CE and ISTJNTUH, please start your presentation, sir. Thank you.
Yeah, thank you, Sushma. On the outset, I would like to thank Professor Himavindu Madam and JNTU for giving me this opportunity. A very good afternoon to all the participants. So my talk title would be Microbial Fuel Cells for the Next Generation Power. Yeah, this is my flow of contents. So I start with certain introduction, and then I would let you know about microbial fuel cells, and then I would discuss about the factors that are involved in the power generation, and then I would also show certain slides of my research which I have done previously, and then there would be a future scope I would like to share with you what is the future prospects of it, right? So as we proceed, so I would start with the introduction with the energy. Right, we have speakers discussing about energy since morning, but in a different dimension, I would like to present it that this is the data of the statistical review of energy in 2019, the global energy used by source. On the x-axis, you can see the time in years, and in the y-axis, you can see the million tons of oil equivalent, the energy which is being consumed by through the years. And it is very well the market, the current scenario is highly dependent on the fossil fuel based society, where you have oil and the other forms of energy which is been there. And you can see the thin line of orange which is passing through, the one which is from the renewable energy sector. So from past 1 decade or so, there is an appreciable improvement in the renewable energy sector. We have different forms of renewable, and one fraction of bioenergy is also one of the renewable form of energy which is contributing to the renewable sector. Hopefully, it may also rise with years to come. That is the hope which we have. Other data which I want to share on the screen is the global primary energy demand. This is the data from the Global Energy Outlook 2020, where you can see from the historical trend the data which is available from 1990 or so to 2020 50, which is the projection which has been made. So this is the black line shows you the energy, which is quadrillion British thermal units of energy which has been consumed, and these are certain projection lines based on the policies and the kind of forums, different forums where they discuss and how the projections are being made. And it is usually expected to rise because the increase in the urbanization, industrialization. So it is usually expected. Exceptional in certain empirical calculations, they might have found that there would be a little bit because of some other reasons maybe, but mostly it would rise, right? And another information which I want to share it is global net carbon dioxide emissions, which you can see here again, billion metric tons of carbon dioxide which has been emitted. This is the trend which is there from past to present, and these are certain projections. And there are some promising policies or some discussions based on which these empirical calculations resulting showing there is a downtrend of the carbon dioxide emissions, where it's a kind of a hope for us that if these emissions are reduced, because naturally you know very well the fossil fuel based society, naturally you have emissions of high carbon dioxide being there as a product, and this is a greenhouse gas, carbon dioxide. So it is always advisable to reduce the concentrations, and these are some certain hope of the based on the technology and everything. This is the hope which we have. This is the data which I want to share of carbon dioxide concentrations, which is called as the Keeling curve in terms of parts per million, where it is measured at Mexico Mauna Loa Observatory. So basically, you can see the concentrations have exceeded beyond 415 ppm. Maybe if someone of you must have seen in certain media and all, there were so many articles published last year, even this year as well, that the concentrations have exceeded 415 ppm, which is a very alarming rate of carbon dioxide concentrations in the globally. So that has to be mitigated, which is a the pressing problem is the carbon dioxide concentrations. And then I would like to share another data. This is the water and energy sector withdrawal and consumption data, which is again taken from the International Energy Organization Association data. So if you see this particular graph, which is from 2016 to 2030, this is global water withdrawal in the energy sector. That is how much water is being withdrawn in the energy sector by the fuel in the sustainable development scenario from 2016 to 2030. So you can see here the the biofuels, that is blue color, which is in 2016 component, which is less. By 2030, the fraction is increasing, means the consumption water withdrawal would be on a higher side, right, in relative to the other which is present, right. So we are projecting that currently now we have power generation by the coal thermal power plants, and probably you have a replacement by the biomass as well as the biofuels, which is an appreciable data. And then you have global water consumption in the energy sector. So again, if you see here also, the amount of water consumption, especially in the biofuels, initial now at 2016, the situation is certainly of this amount, and by 2030, the consumption of water would be very high, because the reason is, if you see the biofuels, major fraction of biofuels is from the like whatever research has been projecting, it is from agricultural waste, basically agri bio waste or lignocellulosic cellulosic biofuels kind of thing, right. So alternatively, we have to look for other kind of biofuels or bioenergies, basically, where water clean water usage will be minimum, and as well as we'll have good amount of energy production. So in that direction, basically I am working on. So there is a water energy challenge which is also posted by the World Bank, which is there, that it has both, we have challenge for electricity as well as for the water which is present, right. And basically I would like to say that there is a there is a closed loop, climate, energy as well as the water is in a complete closed loop nexus, because if you are working with fossil fuel based energy, then naturally there is would be a demand and extraction because of the urbanization which is increasing, resulting into scarcity and demand. And later on in this process, you may also require, you'll be using water as well. So this cycle also continues, and you have depletion of clean water and depletion of energy sources, resulting in the carbon dioxide emissions and eventually affecting your climate. So all these are simultaneously influenced, right. And I suppose most of you must know her, probably Greta Thunberg. She is one of the young environmentalist who has raised her voice in COP25 meeting, basically to reduce the carbon dioxide emissions which are there, right? So like that, we have so many environmentalists who have raised. So she was one of the girl who was actually focused on the problem which is there, and people are working on it. And every year or so we have meeting. Maybe because this year we are facing the pandemic situation, so it is postponed for the next year. So that's how they come gathering, and accordingly they will tell what is the situation and how the countries has to mitigate for that. And we will be dealing with certain technologies. Maybe these which we are presenting are at now at lab scale. Some of them have gone to industry level also. I will share even that. And then yes, surely in coming few years, or maybe by 2030 itself, we will have so many biotechnologies coming into the realistic large industrial scale, and we'll be using it soon as well. So now I would like to share my research area, that is bioelectrogenesis. So this is basically a typical microbial fuel cell diagram which you see. So as the term says, bioelectrogenesis, bio means life, electro, which is something related to electrodes, and genesis is something which is the beginning for some kind of a process. So we have this typical fuel cell where we have the anode at the bottom and the cathode at the top, usually placed. Bottom basically we place it because it should be maintained in the anaerobic conditions, where the oxidation of substrate basically takes place. And at the cathode we have the oxygen reduction reaction taking place at the cathode. And this particular microbial fuel cell, it was in somewhere around 1955 or so, if I'm right, probably. MC Potter, he is one of the first inventors of this microbial fuel cell. And later on, there were so many other proposals, as well as some discoveries and certain changes which is put on this microbial fuel cell. And this is one of the schematic diagram. Whatever may be the changes, this is the schematic diagram, that you have two electrodes, you have certain biological organisms involved in it. That is why it is microbial fuel cell. And when you close this two electrodes, there is an observation made that the electrons from one electrode reaches to the other electrode, the cathode. And that's how it is a microbial fuel cell. Let us try to discuss about the mechanism part of it. So basically, you have this two electrodes, anode and cathode, and the basis for differentiating anode and cathode is because of the electrode potentials. Basically, every material has its own potential as long as it is conductive in nature. So based on the electrochemical potential series, every material has its own potential. So this particular material, when it is immersed in a solution, so its properties, electrochemical potential varies. And similarly, this particular electrode, when it is put in a different solution or a different condition, then accordingly its behavior, according to the electrochemical series, the behavior varies. So now for which will decide anode and cathode depends on the potential. So this particular electrode, which we so called as anode in this particular schematic diagram. So this particular electrode, over which you have this bacteria basically forming a biofilm over it. And this bacterial biofilm is basically forms. Why bacteria attaches, we'll see, get to know as time we proceed. So basically, bacteria, they try to attach to certain surfaces. So if they attach to this, they form of the biofilm of it. And usually, it is believed that the electrogens, or the anode respiring bacteria, basically through which they share the electrons, and accordingly they try to survive. If this is a kind of a metal reducing electrode, then probably these would be respiring by sharing the electrons, and accordingly oxidizing or reducing it, and accordingly giving the electrons. Unlike if not the metal, maybe we can use graphite also. We have also used graphite, carbon cloth, stainless steel mesh. Such kind of any electrode material can be used. And accordingly these bacteria which are which form the biofilm, they basically shuttle the electrons based on the metabolism. You can see the metabolism here. You have the glucose, and accordingly when it is been biochemistry of it, if you see metabolism, so you have oxidation reduction reactions happening. So in this process you have the protons and electrons being released, and basically based on the membrane bound proteins which you have, so they accordingly get shuttled to the anode, and accordingly they move these electrons through the external circuit. They go towards the cathode, and in between the two electrodes you have a membrane, that is proton exchange membrane. Usually these membranes are pre-treated. These are commercially available as Nafion membranes sold by Sigma Aldrich, and very commonly this one is sold. Maybe other companies are available, but Sigma Aldrich is one of the company. And these are basically pre-treated so as to, along with the sulfuric acid and H2O2, hydrogen peroxide, basically to activate the membrane with the sulfonate groups, so that it tries to drag the H plus ions towards the other side of the chamber. And because of the difference in the potential, and because of the presence of electrons and the protons in presence of oxygen, basically the reduction reaction takes place, and that's how you get to the water which is being released. And this mechanism of electron transfer is basically which is available in literature. We have two very well known types of electron transfer. One is direct electron transfer, the other one is indirect electron transfer. In direct electron transfer, basically these membrane bound proteins are involved in it. Whereas in case of indirect electron transfer, you have certain redox mediator shuttlers, which are released, like for example, like Pseudomonas species, which they relieve like phycocyanins and other certain compounds, redox compounds. They take these electrons and accordingly they shuttle with that of the anode electrode which is present. And why they shuttle, it is the complete process that drives is the electrochemistry part of it. That is of difference in the potential. That is the driving force for this electron shuttling and everything which is happening. And another one of the direct electron transport mechanism which is very nowadays very much interesting and hot topic of research is the nanowires. So you have certain small hair like structures or bacterial appendages, especially found in the electrogens, especially like the Shivanella species and Geobacter species. So these are pillay-like structures or hair-like structures. So these are said to be nanowires, and they shuttle these electrons. As we proceed the slide, I will provide more information about nanowires, which is one of the interesting topic. Right? This is another view point which I want to share, is that how the engineering point of view, if you see, there is a triple phase boundary which is actually acting. So what is a triple phase? It is solid, liquid, and gas. The solid is the electrode, liquid is the color electrolyte which is present in the medium where the electrode is being immersed, and then you have the gaseous medium, that is the electrons and the protons which are in the gaseous phase, which tries to pass through the protons. If it is a proton, then it tries to pass through the proton exchange membrane and accordingly go. If it is a electrode, then it tries to diffuses into the electrode and accordingly passes through the external circuit and reaches to the cathode surface. So this mechanism of triple phase boundary happens at the anode side as well as the cathode side as well. So certain people initially they used a catalyst, platinum based catalyst, to catalyze the process of reaction. But eventually with time, they, because of the economics and cost economics and other situations, people have started using only biological catalyst, or that is the bacteria, either in single form as well as in mixed cultures. And accordingly, based on their application, based on their interest of study, the reactor medium is designed, and accordingly the cells are accordingly studied. And this is the one of the schematic diagram which I'll show in especially the Shivanella species, which is very commonly cited. So this is a proposed mechanism. Now, like we have this membrane-bound proteins, and based on the metabolic activity which is happening, even in these proteins, also because of the difference in the potential, the electrons are shuttled outside the cell, and H plus ions to balance the charge neutrality. The H plus ions also are pumped, and accordingly you have this proton and electrons which are in through the reactor medium, and that's how we are harvesting. So as I told, this is the driving force equation, that is delta E is equal to, that is the standard electrode potential is equal to cathode potential minus the anode potential. So you should always have cathode at the higher side and anode at the lower side. It means that this is at the oxidizing end, this is at the reducing end. Greater the potential difference between these two electrodes, greater is the energy which is you will be getting. So that's why both anode as well as cathode both are equally important. Then these are certain. This is one of the side which I want to share, is that this is a per diagram for the criteria for the bioinodes. Basically, as we have seen in the previous slides, we have seen that the biological organism, the bacteria, basically tries to form a biofilm over the anode surface, which is the first criteria for the microbial fuel cells. So for formation of a good biofilm, so these are certain criteria which are been employed or reviewed and accordingly available in literature, that if we can change the surface design or modify the surface design of the electrode, then probably we may increase the performance. The overall aim is through increase the high volumetric power density or the current density which we have, and either by the surface design modification or by the structure design. So if you see the structure design, we have pore size, pore shape, macro porosity, accessibility. So if their pore size are very small, then you can increase the surface area of the electrode, right? Pore shape again, it may be circular, it can be of rectangular, triangular, star shaped, any kind of that kind of. You can make certain difference. So naturally, when you have pores, so there is an increase in the surface area. And accessibility also, it is important that when you have such an pores, naturally there would be better accessibility of substrate, better accessibility of the microorganisms to accordingly form the biofilm on it. More the surface area, more is the biofilm formation, better is your current which is there. But at the same time, what has to be taken precaution is that you have to make sure that doesn't clog the operation. Means with time it should not become a hindrance. So you have to design the electrode in such a way that it surface area should be high for biofilm formation, but it should not clog the surface. Alternatively, suppose if you are aiming at surface design and modification, then you have to make sure that the electrode is highly conductive in nature, and the porosity could be micro porous in nature. Basically you can increase your roughness, that is the surface area, increases surface area, and importantly hydrophilicity, so that more and more organisms can start forming the biofilm in it. And then you have the biocompatibility. This is also equally important. Certain surfaces which you are using, either metallic surfaces or such kind of surfaces, maybe with time that can become toxic to that particular bacterial biofilm which is there. So you have to see the compatibility issues as well of the microorganism. Then charge storage. This is also one of the important parameter, that as we proceed, I will let you know in microbial fuel cell how charge storage is basically done. So these properties we have to keep in mind and accordingly make the surface design and modification, resulting in a microbial attachment for extracellular electron transfer. And finally, that will result in a high aerial current density based on the true electrode surface. And eventually, you have high volumetric current density, ampere per meter cube. So when you talk about scale up and pilot plant and all, so we usually talk in terms of volumetric current density. As you scale up, how whether it is increasing. Objective is to increase, and these are certain strategies where certain attempts where you can improve the uh, anode design. Basically, I'm just talking about the anode design. Yeah, this particular slide which I want to share especially, so this actually makes me this particular area microbial fuel cell, it makes me very fascinating and interesting and challenging as well. The reason is because of this interventions of so many areas of research. It is not sufficient to have area in one particular specialization. People working with microbial fuel cell should have an idea about different concepts of say starting with basic in bioelectrochemistry is required. That is obvious because the you're dealing with the electrodes. That is the basis of it. And you need to have some idea on design engineering, how you react, how do you design the reactor, whether it is a batch process or a fed batch process or a continuous process based, right? And at what distance you have to place these electrodes, whether you have to use membrane or not, if membrane is used, whether it is pre-treated, untreated, or what is the porosity of that particular membrane properties. So membrane engineering comes into picture here, right? Electrochemistry comes into the picture. How electrochemistry is the pure electrochemistry of the of between the metal electrodes. Bioelectrochemistry is something which is slightly different, and that's what people are actually working extensively on bioelectrochemistry. That the behavior when the biofilm forms over the electrode surface, especially changes, and that is very very hot topic of research where people are actually working on it. And you should also have certain knowledge on the electrical analytical chemistry, of course, because there are several products which are being released. So you need to have good instrumentation knowledge on what is your product of interest, how you are basically you know able to what byproducts are producing, whether it is toxic in nature or whether it is non-toxic in nature. Then you should have idea about material science when you're dealing with electrode fabrication, whether how conductive the electrode should be. Should we use pure electrodes or should we use that kind of amalgams or some kind of a mixture of electrodes, composition of electrodes. People have made actually people have been working on of different diverse areas, and accordingly there are different types of microbial fuel cells which are available in literature. And of course, when you are using to treat wastewater, microbial fuel cells to treat wastewater, then you should have certain environmental science background knowledge also, because what is the wastewater characteristics, physical, chemical, biological characteristics, and what are the parameters that have to you have to look so as to make sure that before the treated effluent is discarded into the open environment, whether it is eligible or not. Then obviously it is microbiology. You should have information, good microbiology information, because you are all dealing with microorganisms. Yeah, microorganisms over anode are there. Microorganisms are also there on the biocathode also. I will discuss regarding this biocathode also in the coming slides on where I present my research. So that's how this is the kind of, so that is why I would say that students and those who are interested in doing the research of the interdisciplinary areas are highly welcome, because having expertise in all this area for one particular individual, it is highly challenging. So when we work in team where people from different expertise join together, then accordingly we'll be able to successfully come out with a proper solution. And people are there, certain groups are there. That's how we'll see as we proceed what are the future prospects, how we're successful in getting commercializing microbial fuel cells. Yeah, I will just briefly, give you certain information, because I felt this is one of the area on for nanowires, which is very hot topic of research, especially for students who are the younger generation to pursue their future career in PhD or a postdoc, maybe those who already completed their PhD. So these people are working on these bacterial nanowires. These are basically electrical, conductive appendages, basically produced by commonly by this Shivalla and Geobacter species. They are basically, if you see the structure, they're like hair-like structures, arpillary-like structure, which are said. And these are the species, Geobacter sulfuridations, acidothioBacillus species, spherodoxins and all. So they basically do the extracellular respiration, and accordingly they conduct these electrodes towards the anode, the electrode surface, which is there. So this is the mechanism which was reported in the literature, that they have proposed that usually there are two types of mechanisms. One is metal-like conductivity. So the pili-like structure itself acts as a wire, and based on the overlapping pi electro orbitals which are present between the atoms, allows the electrons to be shared freely and flow between the orbitals. So basically, between the pi orbitals, they overlap, and accordingly the electrons are shuttling towards the electrode from the bacteria. The second mechanism, they say electron hopping mechanism, where the proteins involved in the pili formation, they contain the iron containing heme proteins, and because of that the cofactor iron which is present, so there is a redox nature which is developed, and accordingly electron hole concept is there. So accordingly they get excited and starts moving, they just jump or hop on, and accordingly they from the bacteria towards the electrode, they keep on moving their electrons. This is also one of the other type of bacteria. Those are called as cable bacteria, which is commonly D-sulfobulbaceae bacteria. These are also present in the sediment of seas and ocean, and they are said to be cable bacteria because they form long cables, and because of the oxidation of the sulfur dioxide, sorry, hydrogen sulfide. So in this process, using the periplasmic membrane which is present on the body of the bacteria, accordingly the electron shuttles through, and that's how you can see here the fluorescent image of this um, bacterial cable bacteria, which has formed like a thin wire like structure. And there are reports and good literature which is recently coming up on cable bacteria for proposing for the bioelectricity generation. Lot amount of work is going on in this direction. um, okay, fine. So having discussed about the prospects of microbial fuel cells and their potential aspect of it, I would like to, before we proceed further, we usually have an ideal concept that uh, you know irrespective of any change in application of resistance or load, there should not be any change in voltage that is being generated. That is theoretically desired. Ideally it is desired like that, but what is the reality is that when you apply certain load or resistance, then in the fuel cell this particular behavior is actually noticed, which is called as bielectrochemical losses or the polarization losses. It means that when we apply a resistance or a load, so there is a drop in voltage, you can see here, initially to certain extent, and then you have the slope is not that higher, and then again you have a drastic reduction in the voltage happening at this particular point of resistance when it is applied. So this is commonly called as a polarization curve. So how do we do? Basically, we take the fuel cell, microbial fuel cell, connected with the variable resistance. We get variable resistance in market, and accordingly we set at one individual resistance, and accordingly we ramp with that of the uh, microbial fuel cell. So initially at high resistances, so naturally there is no current flow. So you have good amount of cell voltage. So this particular value is nothing but the open circuit voltage. As the resistance is being decreased, so there is a flow of current that is being observed. And eventually what happens, initially there would be slow amount of current generation would be very less. At after certain resistance, there would be again a drop in the voltage, and that drop in the voltage resulting in good amount of current which is being generated. And after a certain resistance point, there would be a sudden drop in the voltage, and also there will not be any appreciable rise in current which is there, because all the electrons must have got exhausted, and there is no potential difference also, so there is no use, right? So this is the basic typical curve. So this particular curve is actually linked with, associated with the different losses actually, which is called as activation losses, ohmic losses, and the concentration losses. And the reasons for these activation losses, ohmic losses, and concentration losses could be because of the nature of the fuel cell, type of electrode, type of electrolyte medium, which are conductivity of electrodes, conductive property of the electrolyte, distance between the electrodes, and type of biofilm which is formed, thickness of biofilm formed. So there are substrate and bacterial biofilm affinity of that one substrate. So like that, there are so many reasons attributed for the losses which are there. So we will see as we proceed. So this is the information. And there are certain analysis, especially when you are working with microbial fuel cell. These are some of the common analysis, that is cyclic voltammetry, impedance spectroscopy. These are the electrochemical techniques. Apart from that, suppose if you are dealing with wastewater and other kind of a substrate, then you have other environmental parameters like COD, BOD, VFA, etc., which you measure. But typically, since it's a fuel cell, electrochemical analysis, these are the electrochemical analysis which are very commonly done. Apart from that, chrono and other analysis are also done, but CV and electrochemical impedance spectroscopy are very commonly which has been done. So this is a type of the circuit which you basically see here, circuit diagram. So you have a biofilm formed on the anode surface, and accordingly there is a 3 electrode or sometimes 2 electrode. Usually it is recommended for a 3 electrode setup. The 3 electrode is working electrode, that is the anode, where or the electrode which is forming biofilm, right? Usually for a microbial fuel cell, if you are using bioanode, so that becomes the working electrode. Next, the counter electrode C will be the cathode, and then you have a reference electrode. Silver silver chloride is usually used as a reference electrode to basically judge the potential between conductivity potential between the anode and cathode, and accordingly report to the instrument. Right. So it is basically you should have a working electrode and then you should have a counter electrode. In cyclic voltammetry, basically why we perform cyclic voltammetry, to measure the electron kinetics. We basically do this voltammetric analysis. Why it is essential? To study the whether the electron is being released by the biofilm to the electrode. If it is released, how many electrons are being released, and like whether it is a reversible reaction or a irreversible reaction. So like that, is it in steady state or quasi steady state or non steady state? Like that, there are different kinetics part of it to be studied. That is why cyclic voltammetry is basically powered. So in CV, to perform CV, basically we need potentiostat and followed by a galvanostat. And accordingly, this is an instrument which is available by several other companies like Gamry, Autolab by Toronto. Like that, so many companies, Biologic is there. So this particular potentiostat is used for CV measurement. So this is the typical cyclic voltammogram which you observe for a chemical system. If you're taking ferricyanide kind of solution, we usually a reversible kind of reactions usually happen, because it is a basic property of chemistry is you have a very good redox reactions happening. The reactions are stoichiometric in nature, right? And whatever you are theoretically predicting, you can go close to the reactions. That is the advantage of the chemical system. But in case of biological system, things will slightly differ. So this is the pattern which you have: an oxidation curve followed by a reduction curve. And these are the peaks which shows oxidation peak and reduction peak. So this is the peak currents. So based on peak current, there are certain formula where you come to know how many electrons are being transferred, shuttled. This is the kind of a capacitive current. So capacitance is also required. So that's how this particular curve is obtained when you apply potential. So this is, you can see the x-axis, you have potential. So you apply potential maybe from minus 0.5 to plus 0.5, or or maybe 0 to plus 0.5, or minus 0.5 to 0, or zero point 0.1 to zero point 0.5, whatever may be the range. It all depends on what is your microbial fuel cell design, or at what area you want to basically scan, and accordingly see. So there's a scan rate option in that particular software, how fast you want to basically scan. It is like holding a torch light in a dark room searching for some kind of a item. So you how fast you do it, it depends on the process. So usually for a biological process, the scan rates are very low. Recommended is 1 millivolt per second, something like that, so that because the processes are slow. Right, then you come with respect to, after this you have a linear sweep voltammetry. There's another technique where you have only one of these scans reported, or maybe from the CV also, if you take either oxidative or reduction depending of it, you can do certain TEFL plot calculations. This TEFL plot analysis basically gives you the activation losses. As I told in the previous slide, you have different losses called as electron losses, like activation losses, ohmic losses, and concentration losses. So using this TEFL slope from the sweep voltammetry, you get the TEFL slope using the Butler-Volmer equation. So basically you can calculate the activation losses, and this will tell you can reduce. Basically why we are calculating it, once you get the values, you can do a comparative analysis accordingly, see that what are the factors that are actually affecting the activation losses, and accordingly try to reduce it. Eventually that will increase your performance of the system. Then another one is another sensitive technique is the electrochemical impedance spectroscopy. This particular technique, basically it is applied for even for chemical fuel cells also, and basically to measure the internal resistances in the fuel cell. So here what we do is basically we apply if it is a chemical system, we apply high frequencies, and accordingly we measure the resistances. Here in case of biological system also, we try to apply frequency, but in a very lower side of it. The only reason we apply low frequencies or low scan rate, whatever, is because the biofilms which are formed, they are basically sensitive in nature. Biological species are sensitive to potentials or frequencies which we apply. So in order to not to disturb the biofilm form, because it takes long time to form biofilms, so we don't want that to be disturbed. And then accordingly, these kind of profiles are basically measured, where this kind of a diagram basically you find, if you see this, you get two semicircles or half semicircle of some kind of this one. So this larger portion of curve indicates one type of resistance, that is mass transfer control resistance, and this smaller curves basically indicates the kinetic concept, kind of resistances, where certain fraction could be activation, some could be ohmic losses, some could be concentration losses also. It's a very powerful technique. You have x-axis real resistance followed by an imaginary resistance. Followed to this curve, you have another option for Bode's plot, where you also get a different kind of a pattern, which gives information about frequency and the resistance and all. So basically, we use this analysis in the electrochemistry point. Then I move on to the energy distribution part of it. So there was an research article published by the Stanford group, Stanford University, US, way back in 2013, saying that what if the energy, whatever is being given to the microbial fuel cell, is it all the energy being converted into electrical energy? And it was observed, certain empirical calculations were being made, and it was observed that there is no much amount of electricity. Hardly 20% of energy is actually harvested for this energy production out of 100%. Whatever chemical, whatever, say for example, glucose or sucrose or fructose, whatever substance is being given as a carbon source, out of which only 20 to 30% is actually going in the electricity production. And these are the different losses which they have attributed. So based on this, I will just move on certain slides where I have also performed certain analysis, and a similar kind of observation was made in our lab as well. Right? So there are different losses attributed: microbial synthesis, activating potential, microbial metabolism losses, resistance. Because you don't know whatever substrate you have given, you don't know what a microorganism, how it behaves, whether it is your objective is for electricity production, but this is where so much of losses. Even cathode, you can see here, cathode regeneration. So how important the anode biofilm formation anode. Similarly, the cathode is also as equal, or sometimes in some literature, people have reported that cathode is much more important than that of the anode. The reason being that the reduction only, the viability of microbial fuel cell comes only when the electron which is from the anode is been picked up, and accordingly at the cathode, if there is an driving force for reduction reaction, then only the electron can move, isn't it? So if that is why the cathode is also equally or much more important than compared to the anode. And these are certain strategies which I have picked up from the literature, that how to increase the performance of the microbial, right? So you have different strategies here. So you have increased the anode performance by selection and acclimatization of electroactive bacterial species. That is what I was saying. The electrogens are mainly like the Shivella species or Geobacter species. Apart from them, there are other diversity of we have done in our lab. We have seen noticed that apart from that, there are Pseudomonas and other species. They are also part of microbial fuel cell where they have involved. They have found to show power production, but Shivella and Geobutter species are very widely cited. That is the only point which I'm trying to emphasize. And basically, to increase the anode performance, you can use surface modifications can be made. Like for example, mediator immobilization can be done, or carbon surface immobilization by nanostructures can be used. Metal surface modifications can be used, right? Capacitance of the anode can be used. Capacitance is basically, I suppose most of you will be knowing, it's a like a charge cloud. So basically, the anode, at the anode you have the biofilm formation, and towards surrounding that you have the biofilm, and there the electron cloud, dense electron cloud is formed. So more is the cloud, denser is the cloud, and if you have an effective cathode at this end, then the sustainability of a microbial fuel cell becomes more and more better. So that is why we should have good capacitance. It's kind of a property of good storage, that the anode should be able to have certain good amount of storage of that property, capacitance property. And nowadays with advancement of technology, you have 3D electrodes, 3D architecture electrode. Another. And second thing is that optimization of separators basically. So you have the proton exchange membrane, which I told you. Alternatively, you can use anode and anion exchange membrane or cation exchange membrane. So that is there. Certain people have used, but widely cited as proton exchange membrane. And those are that is very Nafion, which is there basically. It is expensive in nature. So people have been working on this direction where some cheaper source or better source of these membrane, which is more porous in nature, gel like separators, and basically can be used for the transfer of the protons. Alternatively, you can decrease the internal resistance of the microbial fuel cell by decreasing the electrode distance between the electrodes. And you can optimize for the electrode assembly basically. It all, like whether it have to be close or to be far, what distance have to be maintained. It all affects. There are so many literature reporting on distance of electrode from between the anode and cathode, between the membrane, right? If you are using a sediment type of fuel cell, then the distance between sediment and the anode. So these are several parameters which has to be looked on, and any change in that small change in those parameters will have a big impact on the performance of the fuel cell. Then you have increasing ion strength of the medium, right? So conductivity is one of the important measurement, especially when you are dealing with wastewater treatment. If the water is not having good conductivity, then microbial fuel cells may not result to in good performance of it. Then you have to design the media in accordingly, or augment the medium accordingly, where the conductivity of that particular wastewater is improved by changing the ion concentration, adding some certain salts or like that. Then you have enhancing cathode performance. As I told, cathodes are also equally important or more liquid. So you should have high oxygen reducing, reduction catalysts which are present. Oxygen reduction reaction catalyst, basically we call our ORR catalyst. So usually platinum is one of the well cited catalysts. Apart from catalysts, there are other titanium and other mixture of combinations are coming recently, where nanostructures are also coming, where reduction reactions are improved. And then you have to make sure that efficient hydroxide ion transport is there, because when you are immersing the cathode electrode in an electrolyte, so naturally there is a formation of OH ions at the cathode side. So you have to make sure there is no biofouling, means there is no other bacterial fouling at the cathode, and you have to check the pH of it. Decreasing the pH of the cathode may probably increase the performance of the cathode, and also enhancing the the oxygen diffusion property of it. Right? And then fifth one strategy which is there is preventing voltage reversal in the serial stack of MFC. Right? So when you're trying to use in a scale up operation microbial fuel cell, it is important that you either create small cells in multiple. It's usually preferred that you create prepare, or what do you say, fabricate microbial fuel cell in small scale, and then accordingly try to stack up in series or parallel depending on the type of voltage or the current which you are basically looking at. Right? During stacking, it is noticed that what happens is no matter you have a similar kind of a microbial fuel cell, you have same design, same configuration, same materials, same electrolyte, inspired same inoculum, everything same. Also, there is a possibility of difference in the open circuit voltages of one cell, cell one, to compared to cell two. Either one or two might be same to certain time of period of operation. After certain time of period of operation, either of these cell may go down or up depending on the type of operation. In that, at the time when you close these cells, what happens, rather than the electron going into the actual circuit, external circuit, where the load is actually connected for your power production or electricity production, that electron starts going into the MFC, which is connected beside adjacent to it. And eventually what will happen, the performance of the serial stack reduces, for which you have to have certain power management systems. So especially students from ECE, electronics, other interdisciplinary areas. That's why I told you it is not a single branch of study. It is in fact a multidisciplinary challenge. So especially people from ECE, electronics, electrical, should able to design, a good, efficient power management system, and accordingly try to track the voltage changes, and accordingly make sure that the electron enters into the main external loop where it has to be utilized, rather than going into some adjacent reactor, and accordingly reduce the overall performance. So for which you have the maximum power point strategy which is there. So this is what is the strategies which are discussed. So that was the general information about microbial fuel cells and their construction, and accordingly their pros, whatever you have the challenges which are there. So now I would like to share this particular slide which I have worked on during my doctoral studies on three different platforms of acidogenesis, bioelectrogenesis, and bioelectrofermentation. So basically, we start up with microbial fuel cells for the power production, and then we discuss about the microbial electrochemical systems or the bioelectrochemical systems, and for the resource recovery operations. And because we have certain advantages with the microbial electrochemical systems also. So as I proceed, I will discuss further slides. This is one of the slide which you must have already seen from the previous speaker, who is my guide as well, Dr. S. Venkat Mohan sir. So we have basically communicated a review, and we have shown that different technologies of microbial electrochemical systems are based on the type of the influent which you take, and the type of bio-based products which you are basically targeting at. So we start up with microbial fuel cell, a similar kind of a construction which is used for, if it is used for an industrial effluent kind of this one, where only treatment is the objective. For a fuel cell, power is the output, which is the this one. If you are looking at the treatment aspect, then it is bioelectrochemical treatment system, where COD removal is the major target. So at the time, what happens? The time of operation. So a fuel cell, we will see, at a certain time you have maximum power production. After certain time, the power production decreases. It is as similar to that of the microbial S-shaped curve, right? Lag phase, log phase, and then you have stationary phase, and then you have a death phase. But if you are targeting for a treatment aspect, then irrespective of time, we keep on trying to increase it and see that the treatment aspect is generated. Then you have bioelectrochemical system, basically where you are using certain effluents of wastewater and accordingly targeting for certain platform chemicals or precursor molecules, which we already sir has discussed, like the acetic acid, butyric acid kind of thing, which are precursor molecules in many pharmaceutical industries. Acetic acid is used. So we can start generating, producing in this from the bioelectrochemical systems. And there are so many, articles which are published on conversion of CO2 into acetic acid and such kind of thing. Then you have microbial electrochemical cell, basically for exclusively for hydrogen and the methane production, mainly for the hydrogen production, basically. And then you have microbial desalination cell, basically when you have a saline water, then you have the use a microbial desalination cell where you can do the desalination as well as certain chemical recovery also can be made, right? This is the work which I worked with during my doctoral studies, basically. So these are the microbial fuel cells. So in this context, I would like to thank once again each and every time when I present this particular slide, I am really acknowledged to the workshop of IICT, CSR IICT, because we have an in-house workshop facility, so that our work has been minimized in designing and as well as fabricating the microbial fuel cells. So these microbial fuel cells were designed and accordingly operated. And some of the objectives which I have presented here is basically this objective is basically to see that at what resistance, if the microbial fuel cells are closed, we will observe a better power production. That was the objective. And basically, I suppose you know very well, power is product of voltage into current under resistance. Only when you close the circuit under resistance, then only you will be able to calculate the power. And that particular resistance we need to check it. And so for which I have done the polarization study and to check the resistance. So this is the resistance versus power density. So at one particular resistance, that is 200 ohms, I've observed that these microbial fuel cells are found to result in a better power production. So to have a long-term study, we have used these microbial fuel cells and graphite as the electrodes. We have used initially all electrodes as setups with graphite, and accordingly we have run these microbial fuel cells. And I have observed that the microbial fuel cell connected with the resistance, which is operated for long time periods, result in better power production than compared to the other conditions. And you can see the trend, usual typical trend. So same like the S-shaped curve which you have for the microorganism growth. So initially you may have certain lag phase, then you have an exponential phase of it along because you have good substrate conditions there. Then the substrate limitation occurs, then it reaches to a certain peak current, and thereafter it decreases. All depends whether it will retain for long time or not, because the electrochemical properties decide at this particular juncture to whether you have a sustainable kind of a power production or not. It is desirable to have long time periods, but for the initial lab scale studies, we didn't find that. So we have, this is the maximum power which we have observed. Then after certain time, the readings went down. And these were other supporting analysis which we performed, that is anode potential. And this particular anode potential is performed by, that is we use a calomel electrode, and accordingly we immerse, and accordingly we try to take the anode potential measurement to see it's like a health parameter. If the anode is showing good reduction potentials, it means that there is a good biofilm formation. Has happened. Better is the biofilm formation, more is the reduction potential that is observed. So in case of the reactor which is operated with biofilm with the closed circuit at optimum resistance, showed a better anode potential. It means that accordingly the performance was good at that particular condition compared to the other conditions which were studied. And similar to that of the Stanford University, we also made an empirical study for this particular system, where, for example, we have taken a design synthetic wastewater, taking glucose as a carbon substrate to study the kinetics and empirical calculations. So if the glucose, whatever we've given is the 100% chemical energy input, so eventually, there is a drop in the energy recovery, and even in our case also, it was hardly 15 to 20% of electrical energy generated. And these are the different stages how the energy has been varied. And the losses are again implicated to the similar kind of reasons which were given in the earlier slide. So for this, we have carried out certain polarization studies also to study the, because polarization curve basically tells you the amount of losses. So these are the slope analysis for these polarization studies, where you can see here concentration losses, and is dominated over the other ohmic losses and the activation losses. ZCL indicates zone of concentration losses, zone of ohmic losses, zone of activation losses. So it is more of the concentration losses in particular to our microbial fuels. So these losses are not always same in all the microbial fuel cell. It all depends on how you operate, what are the conditions and all. So in my condition which we have operated, these are the losses which I have observed, noted to be. So these losses basically concentration losses because of the biofilm, thickness of biofilm formed, diffusion problems of substrate and product, or the interaction between the microorganism. So we have to find out some other alternatives, for which we have carried out certain other experiments where we try to change the electrodes basically, where one of the system we have used was graphite based system. Other two systems which you have seen here, the A1 indicates carbon cloth. We have used carbon cloth as the electrodes, and other system which in B indicates carbon cloth coated with or doped with carbon nanotubes from Sigma Aldrich, which we have procured. And then third kind of system is the graphite electrode system itself, which we continued. And then the fourth system, we have the carbon cloth system, but the buffer here in this case, since it's a anode cathode kind of system, where you have a buffer here, we have not used any buffer, we have used only catholyte is the distilled water. Here we have the catholyte as phosphate buffer at the cathode side. So there were certain literature reports that change in the catholyte composition also may influences. To study that one, we have accordingly used the cathode as with the buffer. And to our interest, we have also operated this for a long time, and also a different circuitry. OC indicates open circuit mode, CC indicates closed circuit mode, and OC indicates open circuit mode. So initially we have kept this fuel cell open to so that it stabilizes with time. The dip in the values which you see here indicates there is a feed change. All the reactors were operated in batch. So taking concentration of that particular substrate, that is glucose, when it has been reduced to the minimum amount, accordingly the feed chain is being made. And accordingly you can see here, this is for the open circuit. And then when you close the circuit with an proper resistance, and that is which we have used here was like the 200 ohms, unlike in the which was done in a previous polarization study. So initially, when you can see there is a change in the behavior of it, the in the microbial fuel cell system. And initially it is there, and then it reduces, and then again it tries to stabilize back to produce the good amount of potential as well as electricity which is required. And similarly with the other reactors also, the recovery of those fuel cells depends on the type of the condition which has been applied. But yes, the cells were able to revive back again when the resistance is removed, it is revived back. So that's how we have run these particular systems. And then these are certain other supporting analysis like polarization analysis which we have done carried out. So the fuel cells with carbon nanotubes basically resulted in high power production compared to the other conditions which we have employed. This is the cyclic voltommograms which we have performed in our study. Basically, these cyclic voltommograms you can see here. There are peaks noticed with case of carbon nanotubes. Peaks were also visible in a very not very appreciable way in other kind of a systems. But in carbon nanotubes, the oxidation current and the reduction currents were, if you see the overall oxidation current and the reduction currents were also higher in case of the carbon nanotubes. And further to this, I've also worked on microbial electrolysis system as well. The reason why I worked is that since I worked with biohydrogen platform as one of my objective, upon biohydrogen production, there is only 30 to 40% of the wastewater treatment takes place, and rest of the waste which comes effluent which comes from the biohydrogen reactor is mainly containing the short chain volatile fatty acids, basically short chain organic acids like acetic acid, butyric acid, propanic acid, such kind of acid. So I thought, why don't we make use of those effluents for further, reduction and production of this biogas or the biohydrogen, which is one of my interests using a microbial electrochemical system. So I have designed this two-chamber microbial electrochemical cell. The difference which I was noted in my research compared to the other research during that time was most of the studies at that time was reported with anode as a abiotic anode. Basically, they used a platinum based anode and a biocathode kind of thing, or vice versa. Maybe a cathode could be as abiotic nature and anode being in biotic nature. So here, what in my study, basically, I have taken both bioanode as well as biocathode. So in first, I will give the substrate that is designed synthetic wastewater containing glucose as substrate. So that particular substrate overnight will result in volatile fatty acids, and accordingly, these volatile acids will be utilized as a starting compound substrate for the at the cathode chamber for the hydrogen production, and for which biocathode we have used the same mixed consortia, here also mixed consortia. So with time this particular consortia started forming biofilm. Each and every time when we change the feed, accordingly those who survived will survive, others were eventually knocked off, maybe because of the feed change and all, or maybe because they couldn't survive. So slowly the biofilm over the cathode formed, and eventually this particular system became ready for the evaluation purpose. So here we have taken the short chain acids, and accordingly we have applied certain potentials, because the reaction of conversion acetic acid into hydrogen production is not thermodynamically favorable. So why it is not favorable? Because the acids whatever will be produced, they are basically weak acids, and as per chemistry, what we say, the pK values usually like acetic acid 3.5, 3.7, 3.8, like that. So they don't dissociate when they are really put in water. They require certain kind of a base. Accordingly, you have to change the pH and see that it is dissociation. So here, so which we have applied certain potentials to make sure the process is going forward. So these reduction potentials are -2, -4, minus zero point 0.6, 0.81, and so on. We have also tested with further other potentials at 1.2, 1.3, where the water electrolysis, we can see bubbles of water coming here. So it means that is water electrolysis. Through water electrolysis also, there is certain fraction of hydrogen is being contributed. But what happens eventually if you increase the potential? We are not interested in water electrolysis because it's a chemical process. Other thing is that these particular potentials may also damage the microbial biofilm which is formed at the electrode. So that is why we have just kept the potentials up to -1, and at 0.6 we have observed a good amount of hydrogen production as well as the overall cumulative gas production, which I have mentioned here. So this is the fraction of gas compared to the other conditions which we have applied. And this was another interesting analysis which I performed. There were other supporting analysis also. This is one of the supporting, and which is interesting is the buffering capacity analysis. So we have used the auto titrator and accordingly titrated the effluent, anode effluent as well as cathode effluent against a strong acid and base. And accordingly, as I told, the presence of weak acids, especially like acetic acid, butyric acid, so the pK values are accordingly noted by the change in the pH. So you can have pH versus the buffering capacity. You can see the peaks value. This particular peak value correspond to, you know, that of the acetic acid. 3.7 or 3.8, which corresponds to the acetic acid dissociation value, pK value. Right? So peak area indicates is proportional to that of the concentration of the acetic acid which is present. So we have found that the peak area is been decreasing in the cathodic effluent when the potential is being increased, 0.2, 0.4, 0.6, and 1, and as well as 0.8. Right? As 0.6, we have observed good amount of removal than compared to the other conditions which you applied. And if you see the mechanism, it is as similar to that of the microbial fuel cell. But actually, in fact, if you see the literature as it says and experience, my experience is that handling a microbial electrochemical system is more and more, electrolysis cell or the bioelectrochemical system is more challenging, especially at the cathode component when you have the biofilm formed at the cathode component, because here the electrons have to reach. First thing is from the anode. If you are using an bioanode, you should be successful in producing good amount of electrons, and those electrons through the resistance has to come to the cathode, and from the cathode it has to diffuse back using again the membrane bound proteins into the cell, periplasmic cell, and then there, based on the metabolite conditions, metabolic conditions, there's again the hydrogen is enzyme acting. Again, you have the hydrogen production there, and accordingly, those that hydrogen is accordingly evolved. So schematically, to should represent things would be very simple, but in reality, when you operate the cell, it is highly challenging to, especially you have a biocathode operation to run with. Another study which we have carried out is a bicatalyzed electrochemical system cell. So having knowledge about the option for electricity as well as hydrogen production, we have designed another fuel cell kind of a system where we have removed the proton exchange membrane, so as to satisfy the economics, just to see if the economics will be reduced if this is successful for a large scale. And then we have this membraneless condition, and then accordingly we have seen that this particular system can be used for both electricity production as well as for the gas production. And this particular, you can see the schematic diagram of the biofilm which has been formed. So mixed micro sewage sludge is basically used as the consortia, and we have the design synthetic waste medium, and accordingly we have operated this in different circuitry modes: open circuit, short circuit, as well as closed circuit. So for short circuit, there is no point of voltage calculation or power calculation. The reason being we didn't have any resistance. The only objective for short circuit is just to make sure that if resistance is not provided, then would be any electricity generation, or would be there any hydrogen production there, and how is the pattern. So for that purpose, we have run this short circuit. But for power production and all, it is the 300 ohms. So for this particular system, since the configuration has changed, again polarization studies were carried out, and accordingly we have found that at 300 ohms, this is suitable for this particular reactor to run. And that's how we have run these 3 reactors. And this is the certain data results for your information, that this is the open circuit voltage which we have. This is the time axis, and we have noticed the power production which is there, power density. In terms of power density is nothing but power by the surface area of the electrode, right? So accordingly, the power density is calculated. So it is found that you have good amount of power density being formed, right? And then use this, apart from the electricity, you have the gas production also. So especially at the closed circuit, you have good amount of gases being formed than compared to the other conditions which were operated. Then this is particular data information about the specific hydrogen yield. Basically, we calculate this specific hydrogen yield as a point of environmental perspective to see how much amount of wastewater has been treated, a kg of wastewater treatment, how much amount of hydrogen been produced. So for closed circuit reactor which is operated, we have observed good amount of yield than compared to the other conditions which we have run. And this is the another empirical study which I have carried out, that is electron distribution, to just see that how the electrons are actually distributed, where it is basically going, whether it is going into the charge formation, that is for the electricity production, or for the biomass production, or is it for the hydrogen production. So at closed circuit at 300 ohms, good amount of voltage was produced. A certain fraction was used for hydrogen, and very minimum fraction is used for the biomass formation in comparison to the other slide, other other conditions which we have operated. This is another study which I want to share, is that which I have performed was microbial desalination. So unlike a two-chamber reactor, we have designed a three-chamber microbial desalination system. Basically, as I told, there is, apart from the water energy challenge, there is also clean drinking water is also a major challenge. So we had a project with New Indigo. Dr. Venkat Mohan sir had a project. So in that part of a project, we have this microbial desalination process. So here we take the saline water, and we have anode as the wastewater, or the design centric wastewater which we have taken, and the cathode chamber, accordingly we have a buffer solution, or we have another system which we have taken as a biotic system. So this is the schematic diagram of it, of microbial desalination cell. So the variation between these two cells is, this is a biotic cathode where we have used mixed microalgae, whereas this particular system is abiotic in nature, where we have used only the water part of it, distilled water, and we sparge with it with oxygen. So here we have, instead of proton exchange membrane, we have used anion exchange membrane, and this particular salt which we have put the saline chamber starts splitting off because of the difference in the gradient, starts penetrating between, we have the anion exchange membrane and the cation exchange membrane. And at the anode, what happens is a similar process that of the microbial fuel cell. You have oxidation of the substrate happening here, and eventually releasing the electrons, and those electrons to the external circuit reaches to the cathode. At the cathode, because of the presence of the cancertia here, they start reducing these electrons, and accordingly form the product. So what are the expected product? So here you have NaCl. So Cl, when it comes to the anode chamber, becomes HCl, HCl, because you have protons and electrons formed. Electrons are passing through the external circuit. You have protons are getting deposited in the anode because you have used an anion exchange membrane. So you have the chlorides passing from this, because there is no chloride concentration at the anode chamber. So because of the gradient, so accordingly they start moving towards the anode chamber. Similarly, at the cathode chamber, since you don't have any, hydroxide or any other kind of a compound, accordingly you have Na plus moving towards this cathode chamber, and there you have the sodium hydroxide being formed as a product, NaOH, because the electron gets reduced at this particular cathode chamber. That's how you can able to recover HCl as well as NaOH. Apart from that, it depends on the type of the kind of a system which you are designing. This is basically for the desalination. So that's how we can make resource efficient the idea behind using algae basically is that you have to have you can use it for multiple products recovery. We can use that algae. Here I've used a very small cells for the lab purpose, but eventually you can start fabricating a bigger cells. I suppose in my lab already there are scholars working in that direction. And happy to share that this particular work was selected by the New Indigo competition held in 2015, and had a chance to present this work at in Europe, in the Rome. conference, and it was also selected as best work. And eventually we have a project where I suppose most of the objectives have been deliberated. These are certain results of the initial work which I have carried out at ICT. Basically, you have this open circuit voltage which is there, and then you close the resistance. So there is a drop in the voltage which is there, but this may be improved with time depending on the number of days of operation biofilm which has been found. So it is found that especially for the abiotic system is better responding than compared to the biotic cathode system. The reason is well obvious, that is, when you have a biotic cathode, as I told earlier, it is very, very challenging. Creating bioanodes is relatively easy than compared to biocathodes, because at the cathode end there should be a receiving electron, and very few species. It is the same species. Some species are actually named as Geobacter species and Sibyllinus species, even at the cathode end also. But there should be an applied potential in some cases, or maybe some other bacteria is also involved in the cathode sites where the electrons can be reduced, and maybe algal also can be used as a reduction also, as I have used. And this is certain conductivity measurements which I've carried out to just make sure that there is a reduction in conductivity, indicating to that of the the change of the desalination that is happening. So desalination efficiency measured in terms of conductivity. That initially this is the conductivity which is there. So a drop in the conductivity indicates that there is a desalination that is happening. And then we have measured, as a wastewater treatment perspective, we have measured for the COD as well as TDS, chemical oxygen demand, and total dissolved solids. So accordingly, we have observed that systems with abiotic cathode actually resulted in better than compared to the biotic cathode. And maybe further work must have been carried out in order to make better conclusions. Yeah, that was with respect to the work which I've done on microbial fuel cells and bioelectrochemical system cells. I suppose Dr. Smith Mohan sir must have given an elaborative talk, a fantastic talk on biorefineries and all. So our lab where we worked on, where I was fortunate to work with him, we have a different group of students working on different platforms, holistically aiming for a biorefinery concept. So my contribution comes with for the bioelectrogenesis and the bioelectricity part of it, and microbial fuel cell into this particular loop, and a certain fraction of the acids, volatile fatty acid production and bihydrogen production and all. I worked in that platform. So accordingly, there are different groups working on it, and holistic making use that the complete wastewater can be used. The concept is basically to make sure that if this concept fits well in the effluent treatment plant. I will just show you certain slides where people have used actually integrated with the effluent treatment plants in India as well as in abroad, just for the future prospect of it. So that's how we have integrated the for the biorefinery concept point of view. And this was one of the article which we have published, and I'm very happy to share that very prominently the citations are there for this particular article, and we have received an impactful award from the VRT in the year 2017, 2018 for this particular article, and today also very widely said. It means that very active research is going on bioeconomy and the biorefinery aspect of it. And these are certain future opportunities. People have certain aspirations. So at the same time, what is the hope for them is that is microbial fuel cell sustainable? Is it really applicable? So there are certain questions which I usually encounter at certain points. So I thought, let me share this slide that yes, sure, certainly microbial fuel cells have a very good future in coming years to come. He is a Professor Ioannis Aeropolis, basically Ioannis Aeropolis from Bristol Research Laboratory, London. So basically, he started with this kind of small microbial fuel cells, and then he set up a robotics lab. And this is the second generation, or maybe the third generation of microbial fuel cells, connected to a robot where it is a fully functional. And eventually, he has done so much amount of research, and his group done so much amount of research and now he is in a plan of making a commercialized startup in a very large way, especially targeting as a P power, basically using urine wastewater and converting that into an electricity. And he has demonstrated. You can also go through his profile and his videos and all. Very interesting and informative. And apart from that, as I told, there are several groups working in India as well as in abroad. In India, we have very prominently, it is Dr. S. Venkat Mohan sir working, and we have Dr. Professor Gangrekar sir and other groups from Gangrekar sir is from IIT Kharagpur. We have even Das sir lab also works on microbial fuel cells and all. Apart from that, there are several groups, young groups coming forward to work in this direction. And abroad also, we have several groups working on it. And this is Professor Derek Lovely from US, basically, from Massachusetts Institute of Technology, MIT, basically. He worked exclusively on GeoBatter sulfur additions and also on some other strains, electroactive strains. His basic ideology is basically to replace the silicon nanowires, silicon chips in the electronics. Basically, he wants to bring the concept of bioelectronics into a viable situation, especially the silicon which is used in the motherboards and chips. That has to be replaced with using a nanowire, biological nanowire. He also has a concept of using DNA or certain protein combination to use as a data charging, data usage. So many hard disks we use. It's all made up of electronic gadgets, right? So if we can replace those with biological components, then it is eco-friendly in nature, and also you have more and more data that can be stored. So attempts are made in that particular direction to use nanowires. Young students are actually encouraged to work in this area. So much amount of research, synthetic biology and other areas, systems biology, metabolic engineering. So many new areas have been emerged, and you can start working on it. This is one of the information just I want to share, which I found in the literature. It's already commercialized. Aquanox used this particular kind of a model where you have for a domestic effluent which is generated, where you have a septic tank for it in a decentralized manner, and that septic tank can be connected with the MFC, microbial fuel cell, with having proper circuit power management system. And then after that, after the utilization of the wastewater or the treatment of wastewater, you can also have a disinfection chamber, and accordingly, then you can use that particular water for the well water or the leave into the groundwater for the absorption, and accordingly that will go into the groundwater. And this is kind of the microbial fuel cell which they have fabricated, and accordingly they have used for the commercial. You can go through this particular article from Mexico. This is people. So it has already, I can say in abroad, it has already come in the market. And this is another article which I found interesting. You can also go through this one, where they have spoke much about the economics part of it, where in the effluent treatment plant, either as a pre-treatment microbial fuel cell, either at the pre-treatment or at the post-treatment at the tertiary level, depending on the type of wastewater, or you can use it for the sludge remediation also. Like that, microbial fuel cell can fit into effluent treatment plant at any event in between the unit operations. It all depends on the type of the effluent, what your objectives, whether your solid contents, total solids are higher or lower, is the wastewater domestic wastewater or is it industrial wastewater. So they have discussed certain economics part of it, the net present value and IR in returns rate, how it is. So this is they are presenting. This is a very optimistic scenario, and this is the most likely scenario, which is close to the real world. And this is a very pessimistic situation where no, very in a very rare situation that kind of things happen, where you have on x-axis you have Coulombic efficiency, that is the performance of the microbial fuel cell. At the same time, treatment is also one of the challenge, and then you have economics into the picture. That's one of the wonderful paper on economics. I suppose we have another speaker followed to me speaks more about economics maybe on different aspect, but more or less people, especially when it comes to biological systems, nowadays people talk about sustainability and economics life cycle assessment. So that is also another part of it, and people are working on it. And surely, I strongly believe that microbial fuel cells will be coming soon into our daily usage. Yeah. So with this, I would like to thank the ISIT team, my supervisor, and Dr. S. Venkat Mohan sir and Dr. Y.V. Swami sir and the whole team way back somewhere 2015 or so, which we had this photograph. So our lab is quite big, team of 20, 30 members. So all of us work together with a holistic aim of addressing the environmental challenges, realistic environmental challenges. And it was really nice and that opportunity for me to work there at IISc. And finally, I would like to thank Professor Himavinda Madam and the team and the JNTU for giving me this opportunity and presentation. Thank you. Yeah, this is this is the NIT Jalandhar campus, and I would like to make an open call advertisement. Recently, we had PhD intakes. Apart from that, any students interested for pursuing with national fellowships are always welcome. I can make recommendations for that, and even students who have already completed their doctoral studies may also, approach for some projects where we can try for funding. And I'm open for any kind of research collaborative projects or communications. These are my affiliation details. Thank you. Thank you once again. Yes. Yes, ma'am.
Thank you, Nikhil.
Amen.
Hello. Thank
Yes,
you,
ma'am.
Dr. Nikhil. We are looking for, now we will address the questions.
Yeah,
hello.
yeah, sure.
Hello. Thank
Yeah.
you, Dr. Nikhil, for your presentation. So the participants have been sharing their questions in the chat section.
Okay.
So I'll read out these
Yeah.
questions. Mr. Tyagi is asking, can these microbial nanowires be used for the synthesis of nanoparticles and further be used as lignin valorization?
Okay. Actually, nanowires is completely different. Nanoparticles are completely different. Nanoparticle is something which is synthesized mostly through chemical routes. Yes, biological routes are also available, but that is a different entity. Actually, nanoparticle is different entity. Nanowires is something like which I have presented here. Those are actually appendages from the bacteria, and people have studied about their protein. They have tried to understand their sequences and everything. They are trying to using synthetic biology approaches. They are trying to produce those nanowires in larger concentrations. Usually it is produced in very minimum amount or the required amount by the bacteria. So using synthetic biology approaches, they want to produce that in a larger scale and try to go for a commercialization, and so that we to use for the electronics application, bioelectronics application. I suppose Mr. Tyagi must have got to the point.
Thank you, sir.
Yeah.
Next, another participant is asking, how does the selection of particular microbial species affect the efficiency of MFC and a microbial fuel cell?
Yeah, good question. Basically, the type of microorganism affects the overall efficiency of it. And there are several papers as of now. I don't have that information, but yes, change in microbial consortia. If we are taking a single species by species level, at the species level also, or at the genus level also, there are variations. That is, notable variations are there. But when we see as a wastewater treatment point of view, it is always to run with a consortia, group of consortia, because waste contains of several components in it. So it is always go with the consortia point of view. And those should be effectively, what it is those bacteria, whatever is used in microbial fuel cells, they should be of, having those properties like the exoelectrogenic properties where they are able to shuttle the electrons. That is the most important criteria for microbial fuels, for that organism to use in the microbial fuel cell. They should be able to release the electron to the external environment and forming a biofilm over the electrode.
Thank you, sir.
Yeah.
Dr. Ramanathan is asking,
yes.
Please suggest possible ways in increasing hydrogen generation.
Okay.
What about the presence of CO? CO is a high affinity towards hydrogen.
Okay.
In this case, how will you ensure the purity of hydrogen for a fuel cell for power generation?
Okay.
Is there any measurement device you have used to check the hydrogen purity?
Yeah. Hydrogen microbial electrolysis cell for in that study we have used for gas composition analysis. We have used GC, and we have measured the composition of the gases. Usually for a typical dark fermentation, if you see, it is around 40 to 50% around you have hydrogen production, followed by 30 to 40% of carbon dioxide, and some maybe the trace gases. And this percentage of gas is can be improved depending on the type of operation, mode of operation. There are several factors again influencing on that one. Type of substrate affinity to the bacteria consortia which you are using, mode of operation, whether batch, fed batch, right? So many pH of that conditions, whether you are using a buffer or a bufferless medium, like that several criteria come to the picture. If we have made studies, actually you can refer certain articles already published from our lab where extensively Dr. Mohan sir, we had a project on the from MNRE where JNT was also one of the partner project for that one, where they have studied on hydrogen how exclusively the production, what are the strains are responsible, how is the composition ratios, and all such information. It's well published in the literature.
Thank you, sir.
Yeah.
Mr. Kiran Kumar is asking, while operating MDC, how to deal with pH changes in anode and cathode chambers?
Yeah. pH in MDC or any electrochemical system or any system for that matter, pH changes would be there. That is for sure. And probably it all depends again on your system. If you want to use a buffer system so that you don't want much changes, then it is better you use a buffered system where you can use a phosphate buffer system, addition of some phosphate buffer, and you can see, make sure that it is. But we, especially in our lab, basically when we have worked it, we majorly used with a non-buffered system only. The reason being that we used to estimate the buffering capacity analysis also, because they are weak acids. These volatile fatty acids are weak acids. These will be continuously being produced as long as you are operating in an anaerobic system. Volatile fatty acids are the common markers which are being released, and they will try to influence the pH of the system. It is always better that you try to utilize less amount of resources when you're trying to target from a wastewater treatment perspective. If you are targeting for power generation or product oriented, then probably you can use a buffered system where you are trying to get maximum efficiency of your product. Yes, sir.
Thank you, sir. Mr. Pravat Kumar is asking, what is the size of the protein nanowire?
Okay. I'm sorry, I don't have any information, but yes, it is in the nanoscale, because you can just imagine bacteria itself is in micron size. So naturally, the nanowire, the pili structures are much more, very smaller to the micron. So it should be around 10 power minus 7 or 8, or maybe close to 9 as
well. So one other last question. So generally we see the fuel cells have a life, degradation occurs. In this case, in this type of nano wires on this USU bioelectrodes, how is this comparable to the standard fuel cells?
Fuel cells, yeah, good question. So basically, it all depends again on the fuel cell construction. Say for example, you have a pentach cell, so you already have certain chemical in it. So that is advantage of a chemical fuel cell, that you have stoichiometrically. If you've taken, say for example, 1 gram of that particular chemical, you know very well the reactions are very stoichiometric in nature. You know how many electrons can be released, how much time it takes for the reaction, and what is the output which is there, right? For a biological system, this is one of this is what it is. This is one of the challenge that given for a given chemical, for example, like how much amount of current will be produced. That's what I've shown in one of my analysis, which is there. Attempts are being made to improve those efficiencies, but how much time it will be producing, how sustainable it is. It is several other aspects are interlinked to that. But I would not say that this problem is unsolvable. People are trying to making their attempts. In fact, very long time I've just seen that Sony company is also working very exclusive these fuel cells. Even Tata is working on chemical fuel cells, and eventually once this concepts of biological fuel cells also comes into the concept of sustainability, then immediately people will transform the chemical fuel cell into the biological fuel cell. And in fact, I have seen certain articles of Sony. I'm not able to find it recently now, but well back in long time I've seen, maybe it is still classified, that is why it is removed from the internet. But once I have seen that very strongly, that Sony was working exclusively on this microbial fuel cell to initially start up to replace the pentach cells batteries from the batteries which we use in the watches and reactors, because we use very small cells to make use of this waste in a dehydrated form. And the cell construction in would be in the membrane in such a way that when the skin, it comes into the contact with the skin, with the sweat and everything, the fuel cell will absorb the moisture, and then that's how the fuel cell gets hydrated and the reaction is initiated. And that's how the application of watches come into existence. And we have actually tried in our lab with the clocks running with microbial fuel cell, LEDs running with microbial fuels and all. Now the technical challenge is how to design that fuel cell, what components have to be used, how we have to make that a dehydrated cell into a hydrated cell, because biological cells works only in the hydrated conditions. So we have to design that membrane in such a way that that cell gets activated and starts producing the electricity continuously. So I think that is the future challenge of the engineers, young engineers, to come out with certain good novel solutions. I think we are very close to that. Maybe in a couple of years we will be able to get that into market. Yes.
Thank you, sir.
Yeah.
So with that, I know no more questions, ma'am.
Yeah, thank you. So thank you, Dr. Nikhil. You have almost started with the fundamentals of microbial fuel cells, and then almost you have ended up with the challenges posing to the students, the upcoming the research students. And we'll see one day the using of the wastewater or those systems for our electronic gadgets.
Yeah, ma'am.
And sure. Power supply. So that is true from waste to energy. The current situation of lacking of resources, and now we have to dig into our waste to get our resources. Yes. So thank you very much for sharing. So we enjoyed your lecture a lot, and then thanks for Dr. Venkata Mohan suggesting your name. Thank you. For this wonderful lecture. Thank you very much. And I hope the participants will be in touch with you for their. Yeah, sure. Welcome. Yeah, thank you so much. Now we'll invite the next speaker. So I invite Dr. Karthik Rajendran, so from SRM University. Hello.
Yeah, can you hear me?
Yeah, now we can hear you. Okay. So now I invite for your talk, sir. Now Dr. Sushma will introduce the speaker.
Good evening, sir. Good evening, everyone. Dr. Karthik Rajendran is Assistant Professor of SRM University. He has completed his PhD from University of Borås, Sweden. He has the highest number of publications in various reputed journals. He is working currently on biogas production, resource and energy recovery, sustainable assessment, biofuels and bioenergy technologies with organic solid waste treatment. I welcome you on the behalf of CE and JNTU, IST JNTU, sir. Now you can present your presentation. Thank you.
Thank you for the brief introduction, and I would like to thank Professor Hima Bundu for inviting me for this particular talk, and also Professor Dr. Venkata Mohan for suggesting my name to her, I think. So in this particular talk, let me share my screen.
Yeah.
So in this particular talk, I'm gonna Yeah, okay. So in this particular talk, I'm gonna briefly discuss about the of lignocellulosic biorefineries. Lastly, Dr. Nikhil has highlighted the importance of economics and how different groups are working. Though this particular presentation is quite off from the previous presentation, but it will supplement a lot in terms of economic analysis and its importance, how it is being done, right? And also like how we have to translate our work from the laboratory to a industry. So this is the basic aspect where I would like to present on today's topic. Okay. The presentation title, as mentioned, is about the lignocellulosic biorefineries and is it economical. So we can split it into three aspects. The first one is lignocellulose, then biorefineries, then the concept of economics. So we will go through one by one in detail. So the first question is why it should be lignocellulose. What is the problem with our current energy scenario or other problems? So if we start from there, now if you look at our, this is the global energy equivalent, right? So it is mentioned in terms of a kiloton of oil equivalent. So if you look, majority of our energy sources is being used by coal, natural gas, and oil. So all these constitute more than about 70 to 80% of our energy usage, right? So the problem comes in terms of the usage of fossil fuels leads to more emissions. So a suitable alternative is what we are looking for. And if you look at biofuels and waste, they constitute around only 10% of the net emissions, net energy that is produced from. So in total, if you look at, there are 14 million kiloton of oil equivalent energy is consumed. And if you look at the share of energy consumption, let's say we are in 2018, majority of our shares are from petroleum and liquid fuels, which is 32%, while coal is the second major contributor, about 26, natural gas at 22. But when we move forward to 2050, the things might change where the share of renewables is likely to increase, maybe double around. But the Sustainable Development Goals of United Nations suggest us to double the renewables by 2030. But if you're looking at this particular picture, we still are yet to double even by 2050, right? So, but whereas the coal concentration, it decreases from 26% to 20%. So this is the way like coal will be because of the renewable electricity. We are changing our electricity patterns from coal to, we are moving away from coal to solar and other forms of energy systems, wind and other renewable energy systems. However, if you look at the share of nuclear, this is a very, very minimal. Even today and as well as in the future, it will be very minimal. That nuclear will be a byproduct or a secondary level of energy production, right? So now we are in the amid a big COVID crisis, and if you look at the crude oil production, you can see a trend what is happening around the oil industry and the market. So if you look at it, first let's say like in 2018 and 19, averagely per day around 100 million barrels of crude oil was produced, and since the start of 2020 due to COVID, you can see a very sharp decrease, and now we are producing only about 80 to 85 million barrels per day, and this recovery might take us some time, right? This is a quite similar trend if you look at the 1970s and 18 great oil barriers. So it is the same kind of situation that is happening in a similar trend. And if you look at since 2014, the oil prices, or 2015, the oil prices have been falling down. Okay, so though the average is there, so because of the COVID, the net energy consumption and the uncertainty around the oil market is happening. And our oil production versus carbon dioxide emission is directly related. The global carbon dioxide emission is in the blue line, you can see here, and the global oil production is in the red line. So as the carbon dioxide, as the oil production increases, our emission for carbon dioxide increases steadily. Okay, so if you take different fuel sources, let's say coal. So if you burn 1 megajoule of coal, you will release 112 grams of carbon dioxide. Similarly, the average for any fossil fuel is 90 gram CO2 per megajoule. And if you are burning natural gas, it is a 62. Biodiesel, which is found as an alternative and which has been widely studied in Indian context, is about 56 gram CO2. And usually the ethanol from lignocellulose is ranged around 36. So if you compare from coal or any fossil fuel, it is almost one third of the emission. So we are reducing about 2/3 of the emission when compared with other fuel sources, fossil fuels. So this is why we are trying to look for an alternative, right? But why lignocellulose? So if you look at the share of biofuels alone, how it is going, and you can see clearly from 2000, most of the biofuels are solid biofuels, right? Most of them are solid biofuels in the sense like it is in the form of woody biomass or other things. Liquid biofuels, the share is quite less, and the share from municipal solid waste are all negligible, the waste from. So from biomass, we can generate energy up to 55.7 exajoules per year, which is almost like 25 to 30% of the world's requirement. We can supplement more than 30% of the world's requirement. But why lignocellulose? Every year we produce about 100 billion tons of lignocellulose, which is a wide abundant material across the earth. So this 100 billion tons include where it is coming from and how it is coming from. So around 53% of it is produced in the terrestrial land space, whereas the remaining 47% is produced in the marine environment, right? So we have a huge amount of energy. So this translates into this particular amount of energy that we can produce, 55.7 exajoules per year. And if you look at the ethanol industry as such, right, like ethanol, it has been researched for more than 100 years now. And the first initial research that has been proposed is in 1826. In 1826, Samuel Morey has used alcohol in a internal combustion engine prototype. And in 1909, Ford Model T has released, and in 1920, you have the ethanol blending. And there were several programs across the world that includes Brazilian sugarcane ethanol program and US corn ethanol program, and the blending of ethanol in even now currently in India we blend with our regular petrol and diesel, we blend ethanol. And there are so many modifications that have happened in the ethanol industry where, for example, in Sweden they are operating E100, that means 100% of ethanol. They have modified the engines and the E100 is there, E95 is there, E85 is there. So sometimes the thing is like ethanol becomes a cheaper fuel, let's say, but then the problem always comes in terms of how we are comparing the cost of a production of ethanol with the petrol or fossil fuel. Let's say, for example, now the demand for petrol has gone down substantially, and this leads to the decrease in the cost of petrol. So in this particular scenario, ethanol becomes a very expensive form of fuel. And similarly, if you are looking at when the prices of a fossil fuel increases, right, then ethanol, not just ethanol for that matter, any biofuel becomes a viable alternative. So how this particular changes, like it is a competition, or we are competing with not two different things. It is actually a same thing, the fuel, but then you are looking at a different point of view. The industry looks in a totally different point of view. Their way of looking at the product or the process is totally different from what we usually see in a laboratory. Industries always look out for the profitability aspect than the we look for the scientific aspect, how it is working and why it is working, what is happening, what is the problem, and we try to solve. Industry want to have a particular problem and a solution, which the solution should be a technically viable and economically feasible. So this is the key aspect of a industrial thought process. And if you look at ethanol, the majority of the ethanol is produced in US and Brazil, right? Like most of the ethanol comes from US and Brazil, and India as well produces up to like around 2,000 or 4,000 million barrels per year. Okay. So if you look at ethanol, where it is produced from, we have 2-3 generations of ethanol production. The first generation comes from direct sugar form, which is the sugar cane and corn. So you have the direct release of sucrose that releases the upon fermentation you get the ethanol. And similarly, you can, for corn, you need just additional hydrolysis step and the glucose is released. Then you can go for fermentation. And finally, you can produce ethanol. Similarly, for lignocellulose, you need lignocellulose is a complex structure where you need to break the structural cell wall to release the sugars. So your pre-treatment and followed by enzymatic process is needed, which releases the glucose. And next generation, after the third generation, is like algae, where you can there is no conflict on biomass or land or food versus fuel, where you grow the algae and then you harvest, pre-treat and do the enzymatic hydrolysis. But the problem with this particular industry, or in general with respect to the ethanol industry, is usually you produce a major product, which is ethanol, and then you sometimes produce carbon dioxide as a byproduct. And sometimes if it is depending on the generation, let's say for example in first generation in corn or wheat based process, you produce something known as a distiller grains. But this is another byproduct which can be used as a feed, right? But then the problem comes as how this particular industry can survive. Let's say for example, if we take a crude oil, right? So the crude oil, when you fractionate, you produce different products. It could be fuel, it could be chemical, it could be material. We are producing quite a number of products from a petrochemical industry. And that is the way to the petrochemical industry is surviving. If you take, for example, the cost of ethylene, polyethylene that we are using, it is about $1,500 per ton. Whereas like if you take, so there are many different products, starting from, let's say, the tar that we produce on the road to the pharmaceutical grade, for example, all the wax, paraffin. There are so many number of products that generated from the crude oil. Whereas if you talk about the biofuel aspect or the biomass aspect, so far the emphasis has made only on the fuel side. Not much focus in terms of industrial viable solution has not been looked at beyond fuels. But when it comes to the concept of profitability or the economic viability, this plays a major hurdle how the industry looks at and how the industry solves this particular problem. So that is why we need to change our way of looking at the things of how we see the biomass in itself. We have to change the concept from just fuel to produce of higher value products, and not just a higher value products. Sometimes there is a product hierarchy where you produce more volume and you end up with a less cost, and sometimes you produce a less volume but then you end up with a high cost. So this product hierarchy is always there, and we have to match all these things into consideration when you want to have a viable biorefinery concept. So now let's see why we actually need to have a biorefinery, right? So if you look at the share of different fuels, and you can see here in terms of how the costing is calculated, right? From crude oil, how much is the cost of different product that you get. So diesel corresponds to 40% of the revenue, gasoline corresponds to around 20%, fuel oil is 12 to 13%, LPG is 3%, and then you have naphtha, which is 6.8, and then kerosene 8, and the others or different products is about 12%. But if you draw a similar kind of thing for a ethanol based plant or any biofuel plant for that matter, we end up with only mostly with the product in itself. It could be biogas, it could be methane, it could be ethanol, it could be diesel, and then you may end up with one byproduct, but not a lot. So this is where the robustness of the process comes in. So the industry can survive. For example, if the diesel prices are decreasing, they can change the pathway or something, and they can generate income from other particular products. Whereas in a biofuel concept, this particular balance is actually missing, right? And if you look the concept of how the crude oil versus the cost of different products that has been there, you can see that crude oil price is directly proportional to most of the products. We have mapped the historical prices for dollar per liter. So in x-axis you have dollar per liter, and the top axis you have dollar per barrel, and we have the unit of different things. So this light green is for the ethylene, and the black one for ethanol, and then jet fuel. So though they have different things, but the cost was like you have a direct correlation between the crude oil and the cost of a petrochemical product. So how crude oil is priced is directly affecting the entire way we live our life. So this has been the problem with the way it is associated with our emissions. It is associated with every part that is connected to our life, and this has to be changed, right? So the problem comes in terms of how we are thinking. So most of our laboratory work that we are doing in terms of any bio-based products or bio-based solution is we start with a research problem, we develop a hypothesis, carry out the experiment, analysis, scale up, feasibility study, and industrial process, right? So most of our work we try to go up to the analysis part, or sometimes we go for the scalability, right? Sometimes we do the scaling up issue up to pilot scale. But then the issue comes in terms of where we are competing with fossil fuel, right? So fossil fuel industry is a very well established industry. As I mentioned, this is more than 100-year-old industry. Since 1900s, crude oil has been explored, and this industry has been optimized over several decades, and we are competing with a process which is just like, you know, since 1950s or something, we have started to do the research on ethanol, right? So how are we going to compete with the traditional flow? This is the traditional flow of action, and how are we going to compete with the such a well-established industry? And this has to transform from research to application into the field. So, and it has to be not just into the field, it has to reach a common man in a large scale platform, not just in, you know, like we are not showing only a demonstration plant, but it has to reach to the entire, it should be widely available. So how this is going to reach? Is this mindset, is this flow of action is sufficient? No, the answer is no. So we need to reduce actually, and typically if you look at any process, if you, for example, the vaccination process, it takes about 6 to 8 years or 9 years for commercial availability. And if you take even researchers who we are working on, if you ask a product development how much years it takes time, usually it takes about 5 to 7 years or 8 years to develop a complete product. It is not easy. Most of this, like, you have to optimize so many parameters, so many things. But then how industries are surviving? The thing is, we need to change our way we look at our total experiment, or the way we transform our experiment to industrial process. So this is where, like, you have a research experiment hypothesis, but then as you know, you have a laboratory work, then you have to look for what is the problem in terms of industry. This usually, in, for example, here in the linear flow, it comes in the last part, the feasibility study. Whereas if you take this particular thing into a sustainable optimization, then you do not just the economic part, but also you have to take care of other aspects, such as whether it is a sustainable environmentally, whether there is a policy, because policy plays a major role for a biofuel system as such, because without a subsidy, you cannot compete with the well-established fossil fuel industry. Even if you take fossil fuel in itself, if you take the historical prices of petrol and diesel, there was a subsidy for diesel available for like last previous decades. Now the gap has been diminishing. And similarly, what are all the market constraints, whether you have the sufficient flow of available biomass or not, right? So like that, when you consider all these parameters into a process and then you scale it up, then the process becomes quite easier for industry to take it up, right? You have to look at the technology, you have to look at the economics, you have to look at the environmental aspect. So the solution that we want to provide is the basics is about techno-economic analysis, right? So let's say, for example, if you want to buy a car, and I would like to briefly describe what is a techno-economic analysis. So techno-economic analysis is like, let's say if you want to buy two different cars, and if you want to compare, so what are all the things you will compare? Let's say you compare the front grille, right? And you compare the ground clearance, you compare whether what is the kind of a brand that you are looking for. What are the features that is available, exterior, interior, safety, fuel efficiency, and what is the cost, right? So these are all the different parameters that you look at, right? So techno-economic analysis is the same thing. You look what are all the things that you identified in buying a car. You identified the technical parameters. You identified the fuel efficiency. You identify what is my running cost. You identified what is my upfront expenses. You identified how much is my insurance, how much I should invest on this particular car. It could be any different car, it could be any different brand, but you identified what are all the parameters that actually exist and how you are going to shortlist. It is the same with the techno-economic analysis. You do the same thing. It is like buying a car, but instead of this particular small car, you completely analyze for the whole process, right? So buying the car technically, for example, okay, this much ground clearance is there, this much view I have, this is the boot space I have. These are all technical parameters, right? Whereas the economical parameter is when you go, you want to buy the car and they say that this is the ex-showroom price and then tax and accessories, and then you get the on-road price. So this is known as the capital investment for the industry. And similarly, if you are looking at you have to put the petrol, there is running expenses every year, right? And this is known as the operational expenses for an industry. So buying a car and the complete process is quite similar in terms of how it is dealt, though the parameter in as such identified is quite different. Okay, but when you add both the capital and operational expenses, this is known as the levelized cost. So this levelized cost is quite important in terms of how we are comparing one particular source of fuel with other. So let's say, for example, in terms of levelized cost, you have to compare with any form of renewable energy, any form of fossil fuel. It is not just only applicable to biofuel in itself, right? So levelized cost is like, for example, per megajoule, how much it will cost, or per cubic meter, how much it is going to cost, or per kilowatt hour or per megawatt hour in terms of energy functional unit, how much is going to cost me in terms of everything. You add all the capex, you add the opex, everything included. Okay, so we have discussed a lot about the transformation of laboratory to industry. I'll just like to bring you one fact that we are working for most of the researchers are working for scientific publications, and after publications we put high value on patenting. And what if I tell you that only 5% or less than 5% of the patent that is filed in US generate even $1 revenue. $1 is approximately 70 rupees. So more than 95% of the patent do not generate any revenue. And this particular number, if you take in Indian context, if I remember it right, it is less than 3%. So what more than 97% of the patent that we are filing or whatever we are gathering do not generate any revenue. So why are we doing those things, and how are we translating, or how are we helping the industry in terms of its feasibility? Is it really helping the industry? If it is going to help the industry, it should have created revenue, but it did not happen. So why the industry did not generate revenue, or why the process did not get it? It is mainly because if you look at analyze the reason, the main reasons could be whether it is a technical problem, or it is the economical feasibility, or the government do not give any proper support in terms of a policy aspect. So this could be any one of the parameters why the industry has not exploited that particular pattern for a commercial venture, right? So in this particular work which we have, I'm going to discuss about, we have compared two different kinds of biomass. One is about the banana grass and the other one is about the energy cane. So these two are wild crops which are cultivated for in Hawaii highlands for a renewable liquid fuels or a biorefinery concept system. So if you look at the banana grass, the compositions of them is given here below. So most of them have almost a similar composition. So it has a 10% of cellulose and 6% of hemicellulose, and extract is a little bit higher for energy cane, and moisture is around 69 and 72%. So what we did actually was we developed a complete process of the industry, right? So we have analyzed, we have created multiple product platforms, so which I'm going to explain now. So here you start with, for example, So you have the front end operation. So when you have the banana grass that is coming in, so that is being in like the pre-treatment process or the front end operation where it is getting shredded, and then it is the dilute sulfuric acid is coming in, and you can see that it is getting the dilute acid pre-treatment is going on. And after the dilute acid pre-treatment, then you split the pentoses and the hexoses. Pentoses go for a 5-sugar fermentation to produce acids, whereas the 6-sugar concentration goes for the SSF process to produce ethanol. And then they go for the upgrading system for ethanol recovery. And similarly, the byproducts go into the co-product utilization for electricity generation and wastewater treatment and reuse. So this is like we have simulated around more than 100 unit operation in this particular picture. And similarly, we have tried out for different cases. So what we did was we took the banana grass to ethanol, a conventional product, right? So this is the existing industry which is there, and then we try to look out for different biorefinery options and see whether if any of this particular parameter is economically viable and sustainable for the industry. So what we did was, okay, why not we go for just the ethanol? We can look for ethanol and ethyl acetate. So that is what this pentose fermentation. So you produce ethyl acetate and ethanol. And why not you just skip the ethanol and go produce completely ethyl acetate? But for ethyl acetate production, you need ethanol. So where do you get the ethanol from? So why not you buy the ethanol from a first generation ethanol plant, and then you produce a complete ethyl acetate products, because ethyl acetate is sometimes more cost efficient, or it is expensive. So you might end up with more profit instead of the actual ethanol in itself. And instead of ethyl acetate, why not ethylene or dodecane? Dodecane is a very advanced biofuel that is a linear polymer chain of ethylene when it is go ahead in a temperature process. So instead of this one, why not you actually produce electricity? Why not you dry the biomass and then just produce electricity via a thermochemical process? Why we have to go through all this step of this one? So we try to match out these 6 different scenarios. So if you see the first word, for example, B corresponds to banana grass, and E corresponds to ethanol. So BEA is banana grass, ethanol, and ethyl acetate production. And similarly, we have BEA, which is only ethyl acetate. So if you look at the overall thing, you can see like if you are using a 60,000 dry metric ton of banana grass, then you end up with around 15,000 metric ton of ethanol and some energy and gypsum as a byproduct. And if you are using, for example, ethyl acetate, then majority of the component enters into the ethyl acetate of 10,000 tons, whereas ethanol production is quite less. And similarly, if you look at only ethyl acetate production, right? So if you look at only ethyl acetate production, you produce more ethyl acetate. So, but you have to buy, as I mentioned, you have to buy some ethanol for the reactive distillation process. And if you do for the same for the mass balance on ethylene production, you can see clearly about 9,000 tons of ethylene is produced via cryogenic distillation. And similarly for dodecane, you can produce up to 7,000 tons of dodecane from the same amount. So there are different volume of product that you will generate using the product. And if you are producing only electricity, you will generate about 18,000 megawatt hour. And you can see clearly, like in most of the pictures, this is about 6,000 megawatt hour is the electricity that you usually generate. So you are playing with that 60%. So here you are getting that additional 60% in the form of electricity. But which one is economically efficient, economically viable? So that's what we will look into. So which particular process is economical? So here you have the red bars here represent the return on investment, okay, which is on the left hand side of the axis, and the blue lines represent the production cost, okay, which is on the right side of the axis. So you can see that ethanol production cost per kilogram is about $1 to $1.5 per kilogram. If you are producing on ethyl acetate and ethanol, the cost increases. Whereas if you are buying it from first generation ethanol plant and you are producing completely ethyl acetate, then the product is might cheaper. Whereas ethylene and dodecane, the renewable form of ethylene and dodecane is quite expensive when you compare with fossil fuel based. And producing electricity is quite cheaper in terms of per unit energy. Whereas if you look at the cost wise, right, in terms of revenue wise, so this is the bar that shows how much is the share of production cost and revenue. So the green bar represents the production cost, whereas the yellow bar represents the revenue. So if the yellow bar is above the green bar, that means you are generating more revenue than the production cost. So that means your process is profitable. So first case you can see here, the ethanol case, you can see like you generate up to 92% of the production cost, right? So that means this particular process is a 8% loss. And similarly, if you are going for a different refinery option of ethanol and ethyl acetate, this has a 10% of loss. And only if you are producing ethyl acetate, then it has a 1% profit, more than 100. And similarly, you can check, right? So this has a 70% recovery rate, 62% recovery rate, and 53%. You might be wondering, the electricity is like very, very cheaper in this particular graph, and you can see why the electricity has the lowest form of recovery. The main reason being that in electricity, if you look at the composition of the biomass, it has about 70%. Let me go back. So here you can see. So the composition, the moisture content of the biomass is about 60 to 70%. So if the biomass is dry, then you can look for an alternative of electricity production. So our choice of process selection should be based on the moisture content that is available in the biomass. So sometimes you might have seen a straw, which is a very dry form of biomass, to be converted into we add water to the form and then you do the anaerobic digestion or fermentation. So this might not be an economically viable process because of the reason that it has a very dry content. So in that particular case, if we go for a thermochemical process, it might be a viable alternative, which has to be verified, which has to be checked out. But this is the way we can analyze to understand whether the industry can survive or not. So if we have done these 6 scenarios and we try to understand, okay, the ethyl acetate is a profitable scenario when compared with even conventional ethanol process, or you produce for a higher end process such as ethylene or dodecane. So if you look and we compare the cost of biomass, the procurement of biomass versus the production cost of ethanol. And historically, you can see that the cost of biomass is increasing over the period of time. And because of that, the production cost of the process is increasing, right? So approximately we reported the case about $1 per liter, $1.1 per liter has the production cost. So now the question comes as such, like whether this particular process is environmentally friendly, right? So what we did is like we try to do the carbon balance. So carbon balance is one of the critical parameter how the carbon is flowing around the different process of the industry. So when you have the carbon biomass is cultivation, it sequesters about 190. So this is like for every ton of biomass. So 119 kilogram of carbon is sequestered, and this goes into the process, like for example fermentation, wastewater treatment, boiler for electricity production, etc. So this releases the ethanol. So the ethanol, from the ethanol acids you release back 37 kilogram of carbon. From the boiler, the carbon dioxide is 65 kilogram. Wastewater treatment corresponds to 1 kilogram, and the fermentation corresponds to 18 kilogram. And you add yeast, like the biomass for the initial inoculum for the ethanol production, which is about 2 kilograms. So if you look at the environmental friendly process, I told you that this particular scenario, the BEA is the most economically cheaper alternative. But then you can see in terms of environmental friendly perspective, it releases about 1 kilogram of carbon dioxide equivalent per kilogram when you compared with other process. So ethanol process itself is also negative process, and then the ethanol and ethyl acetate combined process is a cheaper process, a very, very environmental friendly process, but this is not an economically viable option. Similarly, the ethylene production, which is also not a economically viable option. The electricity, it's also not a economically. So one of the most thing is like sometimes we have to think whether is it like the economical and environmental friendliness is a completely opposite direction, right? And this is because we procure the ethanol from a first generation plant, which releases a higher amount of carbon dioxide emission. And we try to compare it with several different products, like for example, how the jet rotor fuel is doing, soya jet fuel, pyrolysis fuel, crude oil, and many different things. And we try to compare it with different kind of aspects and see how the whether this particular process is environmental friendly or not. But when you compare with crude oil and other things, this particular process is environmentally friendly, right? But when you compare with within the biofuel systems, it might not be environmentally friendly, right? So with this, I almost come to the end of this presentation where so we have different aspects that we have to consider. So one is on the technology side, so which is what we have been doing like for several decades in terms of laboratory work. We have been doing the shake flask, we have been doing the pilot fermentations and etc. and etc. We have been studying the gene level information, so on. But then it has to be translated to the industry in terms of economics, whether this particular process is economically viable or not, whether this particular process is sustainable or not for an industry, whether there are any solutions or anything that is available for the industry in terms of a policy aspect, in terms of market wise. So those kind of things are quite important for the industry to survive, right? So we have to actually explore not just the research in the laboratory, but a holistic approach on how the entire industry can survive, the bio-based industry can survive. So currently we are working on different kinds of areas. So mostly with respect to assessing the resources, what is the levelized cost of energy, the costing, energy balances, and also we are having some small experiments going on anaerobic digestion. And so we are working on a holistic approach where we start with the technology, but then we want to bring in different dimensions. So one is the technology, economics, environment, market, policy, and social aspect. Social aspect, for example, is like we have people in our home that we don't segregate waste for just for a simple reason. It is quite tough, right? So how we can deal with those kind of issues and how we can solve those issues, which can lead to a greater environmental savings in terms of the end process for an industry. So we have to include different stakeholder and different approaches, and we have to combine them for a sustainable product or process development. So if any one of us, if any one of you are interested to collaborate with us, you may kindly write to me. And prospective PhD students can apply. We have in our university, we have 2 to 3 rounds of applications per year. Recently, we had ended up a call for. And so if any prospective candidate is interested in this particular area on economics, carbon balance, biofuels and biogas processes, you may kindly contact me. And this is my contact information. And I would like to thank once again Professor Hima Bindu for inviting me this talk. And also I would like to thank Venkata Mohan sir for suggesting my name to Professor Hima Bindu on this particular talk. And I'm looking forward to the questions or comments that you want to, if you have any questions on this particular presentations or information. Thank you.
Hello, any questions?
Thank you, sir. I actually have been asking the participants if they have any questions to share in the chat section.
Okay.
We'll try to get some. So, sir, I had one question. So one of the barriers for this production of ethanol from biomass is that sugars are necessary for fermentation trapped inside the lignocellulose.
Yes.
How do we overcome this?
This is like, that's what like the concept is. We have been looking at the pre-treatment as the effective option. We have been working on pre-treatment for like around the 30, 40 or 50 years. Now, if you look at the actual ethanol industry, what it is saying is that pre-treatment is no longer a viable alternative. We have to actually change the way we look at the process. That is what the industry states as of today, that the process in itself is like the pre-treatment is not a viable alternative. We have to do something else, right? So this is the industry that has took a stand after 50 years of research. But then that is why I mentioned the point that, for example, if the biomass is so dry, then why we have to go for a wet process? And go directly for a dry process, like which is a thermochemical process, and with the biomass which is quite wet, and why you want to make it to a dry process? So we have to actually change the way that we look at the how we see the biomass, and what kind of, it's not just the sake of publishing papers or something, but then a holistic way how we are going to solve this particular issue. So, and which should be transferable to the industry. So that is quite important, I believe.
So now any further? Why are you some question from Kanakaraju?
Yes, madam.
Can you read?
Yes, Dr. Ramanathan is asking, what tool have you used for techno-economic analysis?
So we are using, it's a, go ahead, sir.
Difference between the techno-economic and the life cycle analysis.
Okay, two different questions. The first one, we are using, there are quite number of tools that are available. Most of these tools are not for free, which means that you have to procure the license. So the first tool that we use for techno-economic analysis is the standard, which is used in the industrial standard, which is Aspen Plus. So that is one particular software. And apart from that, there are other softwares which is used in the bio-based industries, mostly is the Intelligence Super Pro program. So these are the two softwares that we use for the simulations and the calculation part. And when it comes to the life cycle assessment, we use one on the OpenLCA with the external database, or you can use Gabby or a commercial platform such as SimaPro. So I personally use OpenLCA, which is what my advisors have recommended. So I am using the OpenLCA platform for LCA calculation. Can you come again with the second question?
Yes, sir. He's asking what is the difference between techno-economic and life cycle analysis?
Okay, so in terms of a techno-economic analysis, what we usually do is you start analyzing the technology. Let's say, for example, you are doing a pre-treatment of biomass for ethanol production using sulfuric acid. You just try to calculate how much sulfuric acid you are using for a large scale, right? And then you try to look at how much energy you are giving into the process, how much energy you are getting out of the process. So if you do this particular energy balance, then you understand how much is the balance between the assets, how much is the energy efficiency of this process. So this is what is known as a technical part. Only technology wise, you are assessing the flow sheet just on the technical basis. And when you come transfer it into how much it is going to cost you, how much is the industry is looking for, how much is the revenue, how much is the rate of return, then it comes to the point of economics. So this is the first part is the technical, second part is economic. And if you are looking for the environmental or the sustainability aspect or the life cycle assessment, that starts with the input data from the techno-economic analysis, which is the mass balance. So first thing is you have to take the mass balance data and then you feed it to the LCA part. Then you calculate the each and every associated emission for the LCA part. So once you do that one, then that is where you get the entire thing, right? So based on that, you get the sustainability assessment. So this is the difference between, in that you have a lot of different parameters for a sustainability assessment. One could be global warming, one could be acidification potential, resource estimation, and one on the carcinogenic. So there are different parameters on that available. Based on what you want to assess, you will get that information. And there is one thing known as a life cycle costing. So that particular thing is quite different from the techno-economic analysis, where techno-economic analysis involves only the cost of ethanol production per year. But then I mentioned in the initial part of my presentation about the levelized cost, so which actually calculates the entire on its full life cycle, how much it is going to cost for the plant. So that is known as the life cycle costing, which is quite in between the life cycle analysis and the techno-economic analysis. So this is the difference between a techno-economic analysis and a life cycle assessment.
Thank you, sir.
Yeah. May
yes.
I ask?
Yes, Nikhil, go ahead.
Yeah, it was a nice talk, Dr. Karthik. Congratulations. I just want to ask, have you come across a powdered alcohol or powdered ethanol?
No.
I just saw some of my students, they were came to me up for a research project dissertation, like with respect to bioethanol, they were one of the challenges transportation of this fuel. So they were coming up with some ideas. Maybe it's already patented or something like the powdered ethanol or powdered alcohol in a dehydrated form, ethanol in a dehydrated form. Is it really possible?
I have no idea about it. I don't know.
Okay, fine. But in a general sense, can it be really brought into a dehydrated form where transportation?
This is what I would like to tell you. Like, if you look at in general the fuel industry as such, the main tricky form with respect to the transportation fuel industry is you always need a liquid biofuel. Like, it has to be in any other form, the industry would have transformed a long way back. The only reason why it could not have transformed, and electric cars which are in a boom across the globe as well as in India, the main reason being that the shift of liquid fuel is cut. So you are no longer interested in the liquid fuel part. So that is why you get much more efficient electricity engines and other things. So far we could not go through, the reason being that you need a liquid fuel form. So if it is in the powdered form, I don't know how it is about the process of combustion engines, how it works, how it translates to the efficiency, and whether it has to be, you need any additive for it, or how it is going to perform with like there is no liquid, and how the engine is going to react to it. So it is it's an interdisciplinary or a cross-disciplinary work, I think. If
okay,
I put the answer to that particular question. But
okay.
Quite interesting topic to explore at least.
That's what I felt it very interesting. But then he told it is some patented which is already there, like I just was thinking, if not ethanol, any other, have you come across any other alcohols like possibly biobutanol is also widely being explored in the ABA kind of fermentation systems.
It is the same thing. Like if you look at most of this process, the industry is actually, even for that matter, first generation industry, the difference between the production cost and revenue is quite minimal. It is like, even if you, for example, let's say like 1 cent, or it is like 1 paise or 2 paise, then that creates the profit actually, or the loss. And that 1 paise, 2 paise difference is actually a huge profit or a huge loss when you take into consideration the total volume. On a functional unit level per liter, this might be like 1 paise or 1 cent. But then when you are considering it into the level of so many million cubic meter per annum, then that translates into the revenue and the profitability. So the industry is very much thriving on the border. That's what my personal understanding over the years, how the industry is surviving, especially the fuel.
But in Indian situation, Dr. Karthik, what is your views? Like, can really ethanol be used as a substantiate blend for the fossil fuels, or are we at what stage our Indian situation is? Are we because there are some articles where like can ethanol be no, like already we are they say deficiency of ethanol for the public consumption, daily consumption purpose. Like, can we really be an alternative?
I think if I understand it right, according to the policy regulation, we already have 5 to 7% or 8% of blending in current in our current scenario, and we are expected to blend by 2030 up to 15% blending. Is what I understood. But
policies.
Policy is strong in terms of how it is going to help. But then if you look where this ethanol is going to come from, so in India, most of the ethanol is coming from the sugar industry, like Sprit Park. So government is procuring directly from them, and we are consuming from them. But if you are talking about the second generation ethanol, then the question comes. So how the second generation ethanol industry is going to survive? And if you look at some of the industries in India which are operating on the second generation, like there are some from, I think, Indian Oil
industries.
They have a pilot plant available, and also Pragmatrix, they are also having a pilot plant available. So if you look at all of them, they somehow have a multi-product pathway. They don't only look at because the industry have understood that only ethanol won't work. So that is why they have translated to a multi-product, because from ethanol you can produce high value products if the ethanol is not available. So because like you cannot stop only with ethanol because of the fluctuation in the fuel price. So it is all like a domino effect where you start from one point, but then you reach up completely in a different area. So that gives you the problem of that gives you a problem as well as an opportunity where you can transform from one area to another. So that particular transformation is happening, and but this particular area as such for the industrial exploration is quite low compared to Western countries. The main reason being that the economic feasibility. We also have a lot of discussions with some industries and scientists across India, but then the first point comes is what is your production cost? Like how much you can produce it for, how low you can produce it for. So the discussion point starts with that particular ending point actually. So then you don't have a further exploration on those things.
Great. Nice. Wish to work with you in any possibilities in MFC. My area of interest is on my electrochemical systems.
No, we have a lot of discussion. We'll work on it. I just came a year back here, so I'm trying to settle down. So we will definitely work on, and the MFC part and the techno-economic analysis. If you just search for literature, it is one of the least explored options.
That's what I'm looking for. Very seldom work has been done there. There's much to explore there in that part.
Sure. We'll work on it.
Yeah, thank you.
Dr. Karthik, how you can see municipal waste or the garden waste in the urban area? What is the potential for that?
That is the same again.
Same, the different types of fuels you have to.
No. The problem with respect to this municipal waste is in Europe actually, if you are dumping the waste into the land, then you have to pay around $75 per ton. $75 per ton. But in Indian context, we don't have any value as such. If I have to tell you, the $75 per ton is more revenue wise. This is higher share of revenue than the biogas you produce from the waste. But that is the way that industry is surviving in Europe. Biogas industry in Germany or biogas industry in Sweden and other countries are surviving with this $75 per ton. But in Indian context, you don't have any value for that because our policy is such that I think now we have some place, maybe 50 rupees or something per ton. Depends on the municipality again. It is not in the countrywide analysis, but then depends on the municipality. It is quite different. So in that particular sense, this is a higher revenue. The share of revenue of the producing the fuel versus you take to treat the fuel is more. So in our country, that big share itself is gone. You have you are very much concerned with the minor fraction. So that is why, like, I put the share of different products. If you remember the slide, how much is diesel generating, how much is petrol generating. So that gives you an idea. But whereas if in the biofuel industry or the biogas industry, this is quite a different style, that you don't have so much of a products or coming up with.
Here, a lot of anti-segregation problems and then management problem.
That comes post when you start the process. Then you start with the issue of segregation and the issue of handling the waste, and the issue of there are so many issues that comes after. And even now there are many works that are being done in terms of segregation wise, like you have the IR sensors and other sensors, which are like, there are so many updates that happen. So that can do the process to some extent. For example, the aluminum cans.
Some are already some technologies are available, but still, if any soil is attaching on the material, then how to recognize that and those issues. But apart from that, at the local conditions, at least we should have and my point of view is, at least we should have some type of pilot plant study then to assess the cost, economics and feasibility. So at the laboratory, before starting work, at least at certain point we can think of your path, like feasibility and technology and the economics. But certain systems you have to proceed till pilot level to get the exact data.
Yes, absolutely.
You can't stop at the laboratory level itself, the technologies. You have to pursue till the pilot.
Yes, but you can identify which factors are affecting. So then you can critically evaluate and then you go for the pilot.
At least a little.
Sir, which factors are profit affecting factors? Yes. Then it gives you much higher success rate.
Yeah.
So that's the point I want to make.
Yeah. So one more thing, actually, this work can be done through software. So due to this COVID situation, remotely the student can work on this type of projects, maybe, and if any students are interested in our department or elsewhere, so they can take up these topics with you, like they can take up as their project dissertation work.
Yes.
Is it possible?
Yes, it is possible. You can ask them to contact me, and we can arrange for a follow-up meeting or something, and we'll try to maybe go for a joint publication or sometime.
Yes.
So that is quite possible, and we can have a discussion on these areas, how to proceed further.
Yes.
I would be open and interested as well.
Oh, sure. Thank you very much. It's another dimension for this workshop. So very nice presentation, and then very good talk. So I think no more questions. I think, Dr. Any questions in the chat? Hello, Dr. Ravi Verma, any? Then I don't. Okay. Thank you, Dr. Karthik. And then, so maybe in future, our students will interact with you for their work.
Thank you very much.
Thank you very much. And our next speaker, actually from 6 o'clock, due to the time difference, she's from, again, Dr. Venkata Mohan, student from Waterloo University, Canada. She will join at 6 o'clock. So we'll break till 5:45 or 5:50. Then we will rejoin by that time. So then we can have our session from 6 onwards. Thank you, Dr. Karthik, and Dr. Nikhil. Thank you very much for your wonderful lectures. Thank you.